This is an introductory course of logic and computer design fundamentals. And today we will discuss in chapter 5, the arithmetic functions and circuits. We will go through the following points: the iterative combinational circuits. Then we will talk about the binary adders. We'll discuss both half and full adders, and also the idea of the ripple carry and carry look-ahead adders. After that, we will discuss the binary subtraction. We will go through the binary adder-subtractors, which is the combination of the adders and the subtractions. We will discuss this for the signed binary numbers by introducing them first, and then we will check both the addition and the subtraction. And at the end, we will discuss the overflow. Then we will jump to the binary multiplication. And once we're done, this way we discuss the main three arithmetic operation, the addition, the subtraction, and the multiplication. The division, we won't discuss it in this introductory course. After that, we will discuss other arithmetic functions that has been designed using the idea of contraction. The iterative combinational circuit, the arithmetic functions operates on binary vectors. We use the same subfunction in each bit position in an iterative way. We can design functional block for subfunction and then repeat to obtain the functional block for the overall function. And to organize this idea, we do this management. First, we define the cell, which is actually the subfunction block. And then we will use this cell to build the iterative array, which is an array of an interconnected cells. An iterative array could be a single dimension or multiple dimensions. It depends on the organization. So this is an example. This is a block diagram of a one-dimension iterative array. The cell being, this is an example, cell 0. It takes the input A0, the input B0, and the input X0, and it produces two outputs, the output C0 and the output Y0. Now, we build the iterative array using this cell by repeating this cell multiple times. We repeat it n times here, starting from this. Now this is cell 0. And then again, we repeat this, but we change the name to cell 1. And so on up to cell n. Now you should notice that if you take this part here, and you thought that this is the cell, now the indexes here is 0, 0, 0, 0, 0, and this index is 1 and 1. So you think that, oh, this index should belong to the next cell. Anyway, it depends on the organization itself, and you should think about that cell first, and then after that, you repeat it n time. This is an example. If you have n equal to 32, the number of input is equal 66. If we assume that n here is 32, then the number of input, if you count all the number of inputs here, it will be 66. Since the number of inputs is 66, if you want to build the truth table, it will be 2 to the power of 66. The equation that you need to produce will be up to 66. It will have up to 66 input variable, whether it's that, so the 66 will be the upper bound. It could be less. And then you will have this means that you will have equation with a huge number of terms. And if you take any design idea that we studied before, it would be impractical. So the idea now of the iterative array makes it easier. The iterative array benefit from the irregularity to make the design feasible. Now, we will use this in many of the arithmetic functions, starting by the functional blocks, which is the addition. The binary addition is used frequently in any architecture or in any computer architecture. We will discuss the half adder, HA, and then we will discuss the full adder. The half adder is a 2-input bitwise addition functional block. So the inputs, you have only 2 inputs. The full adder is a 3-input bitwise addition functional block. So now here's the difference. In the full adder, we have 3 inputs. In the half adder, we have only 2 inputs. After we discuss the half adder and the full adder in detail, we will use the idea of the iterative array to build the ripple carry adder and the carry look ahead adder. The main difference between the ripple carry adder and the carry look ahead adder is performance wise. The carry look ahead adder is better by a degree of magnitude than the ripple carry adder. So we will start by discussing the half adder. It has a 2 input. Each one of these inputs is 1 bit width binary number, which will compose the 1 binary or 1 bit width binary adder. It will perform the following computation. If you add 1 plus 1, you remember from the decimal that 1 plus 1 is equal to 2, but we cannot represent 2 like this. So the idea is if you add 1 plus 1, the result will be 0, and there will be a carry 1, and it will go down to the result. And you can see that this is the representation of the number, the decimal number 2 in base 2. If you add 1 plus 1, so the result is going to be 1, and there is no carry. If you add 0 plus 1, similar to the previous case, the sum is 1, and the carry is 0. If you add 0 plus 0, the sum is 0, and the carry also is 0. So notice the notation. We will assume that these are x, these values are y, and the result is a sum and the carry to the next position. Also notice that this is the least significant, and this would be the most significant. The position is very important when we calculate any arithmetic function. A half adder adds 2 bits to produce a 2-bit sum and carry. The sum is expressed as a sum bit, S, and a carry bit, C. The half adder can be specified as a truth table, as you can see here. If you add 0 and 0, watch where is the sum. If you add 0 and 0, then the sum is 0 and the carry is 0. If you add 1 plus 0, then the sum is 1 and the carry is 0. If you add 0 plus 1, then the sum is 1 and the carry is 0. And the last row, if you add 1 plus 1, then the sum is 0 and the carry is 1. So you notice that we have 2 bits and we have 2 inputs and we generated 2 outputs. Now, this is the half adder truth table that we just discussed. If you use kernel map to try to optimize it, you can have, since you have only 4 rows here, you have only 2 inputs. This is the kernel map for the sum and also for the carry. And you fill it for the sum like this, 0, 1, 1, 0. This is 0, 1, 1, 0. And for the carry, 0, 0, 0, 0, 0, 0, 0, 0. And the indexes of the min terms, you can see them in the corner of each square. Now, if you try to optimize the sum, you notice that you can't but have each one of the output by themselves. But you notice that this is like a chess board, which means that this is either XOR or XNOR. And since if you have 0 and 0, the output is 0. So if they are similar, the output is 0. If they differ, then the output is 1. You know that this is the XOR function. So either you say that this one is X XOR Y from the truth table, or you would say that this one is X bar Y or X Y bar. Similarly, for the carry, you have only this one, and this one is X and Y. These are the half-adder logic equation. You can have multiple half-adder implementation. I listed 6 of them in this slide. We can have or we can drive the following set of equation for a half-adder. This is the implementation using sum of product, which is the one that we discussed in the previous slide. If you want to generate the product of sum, you could do it by getting it directly from the kernel map, by looking at the zeros instead of the ones, or simply you will say that the sum is X or Y. You can see that this one is the term. You have those 2 terms, and those 2 terms in the product of the sum are the one that were missing from the sum of product. And we could represent the carry by having a double bar, and we insert one of the bars inside by breaking the line and changing the sign. It would be X bar or Y bar, all bar. Also, the third implementation here, we did the implementation by having the XOR implementation for the sum as this way. Or you can also have the XNOR implementation of S by having a double bar of the sum in the previous implementation. If you have a double bar here, then you will generate the XNOR implementation, because you know that the inversion of the XOR is an XNOR. The carry is the same. The implementation here is a substitution of the carry C in the XNOR implementation. You can see that we notice here that this term in the carry is the same as the first term in the sum. So we would say that this one is C. That's the only thing that we change in this implementation. This is a special implementation where you have the sum as a function of X, Y, and also the carry, the input carry. The last implementation, we have the C bar function used in a product of sum term. So we will check the product of sum. We have this. And we know that since this is the C bar would be if you apply a full bar above X and Y, and then you use De Morgan law by breaking the line and changing the sign everywhere here. The X will be X bar, the AND will be OR, and the Y would be Y bar. And we notice that this is the C bar now. This one is appearing in the sum bar. So we replace it by C bar. So you can see that we have those implementation. We have also many more implementation of the half-adder. Each one of them, it has its own advantage. Now the implementation of the half-adder, meaning the generation of the block diagram, if we have the sum and carry as this function, then we can use the sum by having, or find the sum by having x and y XOR together this way. And we have the carry as the AND, the ANDing of both x and y. So we have the block diagram by using two gates, XOR and the AND. If you want to use a NAND only implementation of this function, we use the NAND implementation of the XOR that we studied before, this implementation here. And we notice that if you take the output after this NAND, the result is X bar and or X NAND 1. This is the result here. So if you took the inversion of this by taking the full bar above X ANDed with Y, the result would be X and Y, which is the carry. So you have the NAND implementation of the XOR, and you add also an inverter to get the carry. You could also have the, just to remind you what we've discussed before, you can find the function of the sum by using the X and Y using Boolean algebra like this. Now we will move to the full adder. The main difference between the half adder and the full adder is the number of inputs. The half adder have only 2 inputs. The full adders have 3 inputs. So a full adder is similar to a half adder, but include an additional carry in bit from the lower stages. Like a half adder, it computes the sum bits, the sum, and a carry bit, carry. So you can see in the truth table, we have 3 inputs, X, Y, and Z, and we have 2 outputs, the sum and the carry. The positions are important. This is the first bit position, and this is the next most significant position, or the next significant position, the carry. Now, if you assume that the carry input is 0, you notice that the carry input here is all zeros, and you do the addition, you will end up with the same result as the half adder. This is the same result as the half adder. If you have a carry in 1 in the Z, you can generate the output this way. If you have 1 plus 0 plus 0, the result would be 1, carry 0. If you add 1 and 0 and 1, the result would be 0, carry 1. If you add 1 plus 0, that's what we discussed before, that the result is the decimal value 2, but we cannot represent it in binary using this digit. We represent it using 0 and then carry 1. Similarly, if you have 1 plus 1 plus 1, the result would be 3, which is 1, and carry 1. Just remember, if you, in the addition of the bits, you have 2 bits that are 1s, then the result would be 0, carry 1. If you have 3 bits that are 1, then the result would be 1, carry 1. These cases are, this is the case for the 3 ones, it's only 1 row. And these are the cases of 2 ones, they are 3 rows. And you can see, for example, if you take this case, 1 plus 0 plus 1 is 0 in the sum and 1 in the carry. 1 plus 1 plus 1 is 1 in the sum and 1 in the carry. Now, this is the truth table that we just discussed. If you want to find the function, we will use the idea of optimization using K-map. So now, since we have 3 variables, we have 3 variables kernel map. For the sum, we start by filling 0, 1, 1, 0, 0, 1, 1, 0, and then 1, 0, 0, 1, 1, 0, 0, 1. And you can see that this is also the chessboard again. So it's the XOR of three variables, X, Y, and Z. This is the XOR, or you can get the minterm this way, the first one being X bar, Y bar, Z, and then which represent this one, X bar, Y bar, and Z, and then you have X bar, Y, Z bar, or X, Y bar, Z bar, or X, Y, Z. The last one, X, Y, Z, is this one. We can also write them using the sum of minterms 1, 2, 4, and 7. For the carry, you will do the same way. You will put the zeros and ones in the kernel map, and then you will optimize it by having those two together, those two together, and those two together, and you will get an interesting function, the XY or XZ or YZ. It has another name. It's called the majority function, which is a voting function where you count the number of ones. And you can see that the carry is 1 only when the ones are beating the zeros in a voting game. This is also could be representing using the sum of minterm 3, 5, 6, and 7. Now, the equations of the full adder from the K-map, we get those two equations. And as we discussed, that this S function is the 3-bit XOR function, which is X, XOR Y, XOR Z. The carry bit C is 1 if both X and Y are 1, which is the sum, which means that the sum is 2. Or if the sum is 1 and the carry in Z, you have also the carry is occurring. Thus, the carry can be rewritten as X, Y, or X, X, or Y, Z. So the carry function that we said that it's the majority function, it also could be rewritten like this, which is X ANDed with Y, or X, X, or Y, all ANDed with Z. This is an interesting function because now the carry is the function of the X, the Y, the carry N, and also this half addition function, which is X, X, or Y. To make sure that this is also correct, you could prove that this function is equal to this function using the truth table idea or the Boolean algebra. Now, it's good to mention that X ANDed with Y, which is this term, is called a carry generate function. This part here, which is the X, X, or Y, is called a carry propagate function. And we will see this more in the coming slide, especially when we talk about the carry look ahead adder. Now, the full adder schematic based on those functions that we find, the last two functions for the sum and the carry. Now, the sum is a 3-input XOR function, which is A XOR with B, and then you will get the propagate this way. This is what the definition of the propagate. And then we XOR it again with the third input, which is the carry N. So we replace now the inputs part that we had X, Y, and Z. Now they are A and B, which is the two inputs that you want to add, along with a possible carry that is coming to that stage, carry input, or the input carry. So you have A and B and C. To have the sum, you will have the 3 input XOR. This is 2 input XOR, followed by the last one, and you get another XOR to generate the sum. Now, the carry out is the OR between 2 terms. This is the OR function of 2 terms. The first term is Z, or what we said, it's the carry in now. So the first term would be Z. And the second term, or let me do it this way. So just to not confuse you, if we rewrite the sum and carry for those inputs, then the sum function would be A XOR B XOR the carry in the input. And the carry would be A ANDed with B, or A XOR B ANDed with the carry input. So now we represent this in the block diagram. You have A XOR B XOR the carry input this way. You have A, B, and the carry input. You apply them to the XOR, the A and B, you generate the propagate, and then you get the carry input with XOR to generate the sum. Now, you notice that the carry out, which is the generated carry, is A ANDed with B, which is the generate function. This is the A ANDed with B. This is the first term that gets here. So we get the generate first. And then we get the propagate, which is the A XOR B. This is the A XOR B here. We get the propagate ANDed with the input carry here to get the second term that were OR together. So that's the full second term to get the carry out. Now, as you can see, this design is a combination of a 3-bit XOR for the sum and a carry logic for the carry out, as you can see. Also, the carry out is based on the propagate and generate. Again, the propagate is the XOR function, and the generate is the AND function. The carry generate signal, this is the generate is the AND between the A and B, and the carry propagate is the A XOR with B. So this is a mistake. It's supposed to be the AND. The carry out is either generated or propagated from the carry in, and this is the idea behind the carry look ahead adder that we will see in the future, that now the carry out, it has 2 possible ways. Either it is generated in the same stage, you take it from here, or the carry is propagated from a previous stage, meaning it's propagated. So it's propagated from where? From the carry input to the output. So it has 2 possible ways. Either it's generated in the same stage, or it is propagated from a previous stage. So now, the same implementation, now you notice that we have 2 half adders with an OR gate to generate the full adder. This is the functions of the full adder if you use X, Y, and Z, and this is if you used A, B, and C, but now we added the correct indexes I meaning that this is in a certain stage I. Now, if you have a cell for the full adder, you would say the full adder has 3 inputs and it generates 2 outputs. The inputs are AI, BI, and CI, and it generates a sum. SI, notice it has the same index because the sum of the same position bit is generated, and it's also generate a carry to the next stage, the carry CI plus 1. You could have the full adder this way or the other way around, meaning that we make the carry go this direction from the carry input to the carry output, or we make it goes this direction from the carry input to the carry output. So now this is a good conclusion that the full adder is actually composed of 2 half adders with another OR gate. Also, we will apply the idea of the iterative array now. Now, this is our cell that we are going to use, and based on this cell, we will try to use the iterative array method to get the types of the other types of adders. So now we will check multiple bit addition. So the binary adders, in the idea of the binary adders, to add multiple operands, we bundle logic signals together into vectors, and we use the functional block that operate on vectors. As an example, we will design a 4-bit ripple carry adder, which adds an input vector of A from 0 to 3, meaning now A has A0, A1, A2, and A3. This is 4 bits. And also the same way for B from 0 to 3, and we generate a sum vector sum from 0 to 3. You should notice that the carry out of cell I becomes a carry in of cell I plus 1. So now, as an example, we check the table below. If we have this addend, and this is this organ, and this carry in. So the A is 1101, the B is 1100, and the carry in the inputs, which is CI, is 0110. Notice that the first stage, since you just started, the carry input is 0. So now if you add those 3 binary bits, 0 plus 1 plus 1, the result is 0, carry 1. If you add 1 and 1 and 1, the result is 1, carry 1. And if you add 1, 0, and 0, the result is 1, carry 0. And if you add 0 plus 1 plus 0, the result is 1. And there will be another carry going to the next stage, which is 0. And since we are done, this 0 have no value. You can also add it here, but it doesn't have any value. You can see that now the carries that we generated in the next stages here, which is the 1, 1, 0, and also the 0. These are also the carry in the output, as you can see here. So now, to generate a 4-bit ripple carry binary adder, you simply take one cell, which has 2 inputs or 3 inputs, A0, B0, and carry 0, and generates 2 outputs, the sum 0 and the carry 1. Now, the output carry of this stage will be the input carry in the next stage. And you connect them this way. Notice that this index is 0, this index is 1, here is 2, and here is 3. So looking at the operand, the input operands A, B, and C, and also the first result, which is of the first output, the sum, they all have the same index, 0. But the output and the carry, the resulting carry, would be the next index, because you have the carry in the next position, which is having index 1. And so on. So the end result of a 4-bit ripple carry binary adder is 4-bit sum 0, sum 1, sum 2, and sum 3, and a carry in the output, which is C4. This is a ripple carry binary adder, and this is the first type of multiple bit addition. This is the first adder type. It's very famous because the design is very simple. The idea behind it is just connect the carry output to the carry input. Now we will see the carry propagation and delay. The propagation path for a 4-bit carry, a ripple carry adder, is as you can see here. Remember that this is a single bit cell for full adder. You can see we have 2 XORs to generate the sum, and we have a half adder and another half adder and the OR gate that we discussed before, but it was drawn in a different way. Now also this is the propagate signal after the XOR. This is also the generate signal after the AND between the A and B. Now we connected the carry output of each bit to the next carry of the next cell, and you can see that this connection here is going to the input of the carry of the next stage, similarly here and also here. Now, the longest path, or what we call the propagation path, also there is a better name for it, which is the critical path, is going from the input A0 and B0 through the XOR, and then you have AND, OR, AND, OR, AND, OR, chain, and then you end up going through S3, which is through this XOR. You can see that there is a path, or this long path is going from A0 or B0 through the circuit until it's reaching S3. The 4-bit ripple carry problem is the length of the time to propagate the ripple carry from the least significant bit to the most significant bit. So you can see that it takes a long time. Also, if you have several bits, instead of having from 0 to 3, let's say you have from 0 to 31, then you will have a long path of AND, OR, AND, OR, AND, OR. So this will have a bigger delay because of this ripple behavior. And to solve this problem, we could use carry look head addition, or we could use other type of adders. Actually, this is the critical disadvantage of the carry ripple addition. It has a long delay to generate the result. So one idea is to have a carry look ahead adder, and we will discuss it in the next few slides. First, we will discuss the carry, or revisit the idea of the carry propagation and generation. We know that if you have the generation of a certain stage, it would be the AND of AI and BI. If we want the propagation of a certain stage, it would be AI XOR of PI. Now, the next carry equation, the carry out would be either it's going to be generated in the same stage or is going to be propagated from a previous stage. That is the idea behind the carry look head addition. To understand the generation and propagation, here are several examples. This is a propagated carry examples. We have two examples here. If you have a carry input, which is 0, and you have those two inputs, A and B, if you look only at the carry, because the carry has the bottleneck, you see that in the carry ripple addition, the delay was long because of this chain of carries going from the first carry to the last stage carry out. So you can see here the same idea. This is the input in the carry, the first stage. This is the carry input. And then you do the addition, 0 plus 1 plus 0, you get 1, carry 0, and so on. 1, carry 0, 1, carry 0, 1, and carry 0. You could see that this 0 is actually propagating through the other stages until it will reach to the carry output. Why this propagation behavior? Because the propagate signal is satisfied. The equation of the propagate signal is satisfied. So you can see here that A and B is differing because the XOR of 1 and 0 is 1. So the propagation is valid. The carry will be propagated here. Similarly, it will be propagated here. Similarly here, it will be propagated here until you reach to the carry out. This is if the carry input was 0. So here, the 0 was propagated to the output. Similarly, if you have this example, now the propagation of the 1 is happening to the carry in the output and of the last stage. And you could see it the same way. 1 plus 1 plus 0 is 0 and carry 1, and so on. 0, carry 1, 0, carry 1, and so on. Because of the propagation function gives you 1. So it tells you that the propagation will happen. If you have a 1 and you have the propagation satisfied, this 1 will be propagated to the next stage. Similarly here and here up to the last one. So this is a propagated carry example. To have a generated carry example, you have those two. You could see here, if, for example, you have a carry input that was 1 at the beginning, since you have 1 plus 0 plus 0, you have the result is 1, carry 0. The generation is not satisfied, so there is no carry generated here. So notice that the carry is 0 right now in this stage. Now, if you have 0 plus 1 plus 1, the output is 0 and carry 1. And you can see that the generation is satisfied. The AND result between 1 and 1 is 1, so the generation will happen. And here comes a new carry generation. There was 0 before, and now we have a new carry, which is 1. Similarly here, because in the previous stage here, we have 1 and 1, there will be a new generation in this stage. New generation in this stage. So those two bits are carries that were generated. Similarly here, now you have 0 at the beginning because of this condition satisfying the generation of carries. You have 1s in the next carry, in the next position, or carry in the next position. Now, here is a mixed example where you have a generation. After that, you will have you have this generated carry propagated to next stages. You can see that the generation is satisfied here and also here. And because of this, you have 1 in the next bit that were generated. And after this, you can notice that in those two stages, the propagation is satisfied. So this carry will be propagated here and also here. So we have a generation followed by 2 propagation. Similarly here, for same reason, we have a generated carry and then propagated to next stages. That was the idea behind the carry look ahead addition. To generalize the idea and discuss the design of the carry look ahead addition, here it comes in this slide. The carry look ahead adder, it generates and propagates for a group of carries spanning from 0 to I plus 1 this way. The carry of the next stage, which is I plus 1, is either generated in the same stage or it was generated in a previous stage and then propagated to this stage. And we have the same base cases for the generation and propagation. Now, for example, if you want to get the carry in the next, on the second stage, carry 2, then it's either generated in stage number 1 or it is it's the carry of stage number the carry 1 and then propagated to the next stage by the propagation of 1. Similarly, for C1, either it's generated in the same stage or propagated from a previous stage. Now, you can see the indexes here. By looking at the indexes, you can see all the indexes here are the same, while they generated carry of the next position. So if you want carry 2, then everything here is 1. Similarly here, if you want the carry of 1, everything here is 0. So the idea behind the carry look ahead addition is to get the carry of every bit position. So we want to get the carry 1, the carry 2, the carry 3, the carry 4, and so on, based on how many bits you want to bundle together to have or bundle together as a carry look ahead adder. So here are examples. So this is the C1. The C1 is already ready. We just copy it. The C2, we copy it from here based on this equation. And then we notice that we have C1 here. So we take the C1 out and we substitute its value here to get the C2. Now we have C1 already ready to be used. We have C2, but we will distribute the P1 here and here. So you notice that this term will have 2 bits and this term will have 3 bits. Also, you notice that this term here starting from C0 and then P0, P1. The second term, G0 and then P1. And the last one is G1. Notice the similarity. This would be C0, this would be G0, and this would be G1, and so on. And for the propagation, in this term, you have P0, P1. This term, you start from P1, and then you stop, and so on. So now we know for C3 and C4, we will have the same idea. Look at the C3, you start at C0, and then G0, G1, and then G2. And then first one here is P0, P1, P2. Here, P1, P2, and here, P2. An easier way to remember those 3 propagations, starting from the first one doesn't have any propagation because the carry is either generated in the same stage or propagated from previous stages. Either propagated from this stage, the previous one, or propagated from the stage that was 1 bit apart from it, so it needs 2 propagations, or from the beginning, so it needs 3 propagations. You can see that we are going through this P2 going down. P2 and then P1. P2 and then P1, P0, and so on. For the carry 4, you have the C0, G0, G1, G2, and G3. And now B3 going down, B3 and then going down, only propagation 2. B3 going down, B3, 2, and 1. And the last one, B3, 2, 1, and then 0. This is the idea behind the carry look-ahead addition, is finding those terms, and we know now how to find them. Now for the sum is actually the propagation signal XOR with the CI, XOR with the current carry. So you have the current carry that you generated, either C1, C2, C3, or C4, and then you XOR it with the propagation signal that you already defined in the base case. Now, this idea that I just discussed to you, I generalize it for any number of bits. The carry look-ahead adder follow this equation. The next carry, Ci plus 1, either generated in this stage, the current stage, I, or generated from a previous stage. By doing what we noticed in this examples, you can break it into several terms, either generated in the first stage or propagated from a previous stage, or you can see that now the PI, we start from it and then go down. Either it's propagating from PI going down up to P2 with G1, PI going to P1 with G0, PI going down to P0 with the main carry input, which is C0. Now, we will have those equations, C1, 2, 3, and 4, and we will try to draw the block diagram here. Those are the 4 equations that we derived. And now we will draw the 4-bit carry look-ahead adder starting from index 0 to index 3, 0, 1, 2, and 3. So here are some things that you notice at the beginning. You can see that the sum doesn't have any trouble for the carry look-ahead addition, because now this sum is the XOR with another XOR. So it's 3 input XORs that generate the sum. Same idea in the ripple adder. Similarly, for this sum, it's the XOR between this and this, XOR and XOR. So you get the carry XORed with A and B XORed with the carry, and so on here, and here, and here. Also, you see that there is a good organization, the carry look-ahead addition. In this stage here, we have the propagation and generation of base cases. We have P0, G0, P1, G1, P2, G2, P3, and G3, which is the XOR and AND gates for each stage. So it's like this group is the propagation and generation only. The last stage here has only XORs to generate the sums based on this equation. The sum Si is the propagation XOR with the C of I. Now the job of the carry or look-ahead addition, or to be honest, any other type of adder, is what's happening here. What's happening inside. So you can see C0 goes directly to get the S0. Now, our job is to find C1, C2, C3, and C4. And those the equations for each one of them. We basically build each one of them individually to get the carry look-ahead addition. So let's focus on this. For C1, you get G0 or C0 ANDed with P0. So you get G0 or P0 ANDed with P0. You can also notice the idea that we just discussed, that a carry one, it's either generated from the same stage. It's either generated or it is propagated from a previous stage. So either it's generated here or propagated from a previous stage. Similarly, for C2, you can follow the same equation to make sure that this OR and is correct. It's either generated here or it is propagated from a previous stage or propagated from the stage before that, which is from here, and then propagated through the purple and also through the blue, propagated through the purple and the blue, and so on. Let's take the extreme case, which is this one here. You can see that one of the inputs of this OR gate, which is this one, is C0, this C0, propagated through all the stages, propagated through the purple, P0, the blue, P1, the pink, P2, and the red, P3. Purple, blue, pink, and red, and so on. Now you know the idea behind this. Also, there is something that you should notice. For example, if you take C4, you have a 5 input AND followed by 4 input AND followed by 3 input ending with 2 input and then a single variable term. You can see this is the 5 input, 4, 3, and then 2, and this is the single term, G3. Similarly here and here and also here. This is the carry look-ahead addition. Now, if you want to compare this with the 4-bit carry ripple adder, you see that the size is exploding a little bit. It is having a bigger area, more gates, more individual gates that have many inputs. But the critical path is shorter now. This is the critical path. It is going through this XOR followed by 4 input and 4 input OR going to the S3. So it's like having 4 gates to generate the carry look-ahead addition. If you have multiple bits of the carry look-ahead addition, you still have a 4 gates that tells you what is the critical path. In this path, you have 2 that never changes. The XOR and another XOR, 2 input XOR in the beginning and the end. And also, if you compare it to the carry ripple addition, you will have the same thing. But the change is here. Now, as a member of the critical path, you have 4 input and 4 input OR. 4 input and 4 input OR. Now, we will move now to the binary subtraction. After we finish the addition, we discuss the half adder, full adder, ripple addition, and the carry look-ahead addition. We will move to the unsigned binary subtraction. There is something that I want to begin with. If you want to borrow, because we will discuss the borrow idea. If you want to borrow 1 from the position I plus 1, which is 2 to the power of I plus 1, it becomes 2 ones into the next or the previous position, 2 to the power of I. Meaning, if you want to borrow this one, into this stage, then you cross it and you put 2 ones. It's actually the same idea that we took in the decimal system, that we had in the decimal system. The algorithm now is you subtract the subtrahend n from the minand m, and if no end borrow occurs, this means that m is larger than or equal to n, and because of this, the result is a non-negative number and it's correct. You can see it in this example. We subtracted 9 from 7. To subtract 9 from 7, we're supposed to get 2, and we got 2 correctly. The idea of subtraction, we start by subtraction 1 from 1, and you get 0. Now you cannot subtract this, so you need a borrow. You can't borrow from here. It doesn't have anything. You borrow from the last one here. Notice that we borrow this one and we cross it and we generated 2 ones here. And then we cross one of them. I picked this one and we generated 2 ones here. Now I can subtract 2 from 1. To subtract 2 from 1, you get the result 1. And now subtracting 1 from 1, you get 0. And the last one, since we crossed this one, it's already 0. Notice that we didn't borrow anything beyond 4 bits. So because there is no end borrow, then the result is correct. Now, if an end borrow occurs, this means that n is larger than m, as this example suggests. You have 4 subtracted from 7. The n is larger than m, and the difference, this difference, and we will check it later in one of the slides, is subtracted from 2 to the power of n. And then a minus sign will indicate that this result is actually a negative number. To check this quickly, 4 minus 7, the result is minus 3. How to get this in binary? You will try to subtract 0 from 1, and you can't. So you try to get a borrow. You can't borrow from this one. You will borrow from this one. So to borrow from this, you will cross it. You will cross this, and then you will put 1 and 1. And then you will cross one of them, and you put 1 and 1. Now you do the subtraction in this stage. The result will be 2 minus 1 is equal to 1. Those 2 minus this one is equal to 1. Now you can subtract 1 from 1, and you get 0. And now when you reach to this point, we already take this one. So you cannot subtract 0 from 1. You need a borrow, and you can't borrow from here. Now you're done with the number of bits. So you need a end borrow. You generated 1, and you borrow it into the next stages. So this one is going to be 1 and 1, and then you take this out, and you get 1 and 1. Now you have this 1 and 1. Subtracted from 1 is equal to 1. And this 1 and that we already take out. Now you have 1 subtracted from 0, and the result is 1. Now we end up with this result. This result, since you have an end carry, is not correct. To correct this, you generated this number, which is 1 followed by zeros. This 1 followed by zeros is actually 2 to the power of n. And this number is actually taking out from this term. Now you have this 0, 0, 0, 0, and 1, and you subtract it from this number. And you know that the subtraction, you can't borrow anything from here. So you take this out, and you put 1 here, and 1, 1, 1, 1, and 1 and 1. 1 and 1 subtracted from 1 is 1. Here is also is 1. And since you take this 1, 1 subtracted from 1 is 0, and 1 subtracted from 1 is also 0, and the result is 3. The result is 3. Now, since you did this correction step, you know that you need to put a negative sign. So if an end borrow occurs, then n is larger than m, and this difference is subtracted from 2 to the power of m. This difference that you have here is subtracted from 2 to the power of m. The minus sign is appended to the result to indicate that this result is a negative number. Now, these are some examples of unsigned binary subtractions. If you want to subtract this number from this number. This is the minus, and this is the subtracted number. And this is going to be the result, and these are the borrows. So you can see here that first you try to subtract this 0 from 0. You can. The result is 0. 0 from 1, you cannot. Then you need to borrow this one into this 2. Now you can subtract 2 from 1. The result would be 1. And now, in this stage, it's already 0. You cannot subtract it from 1. So you need a borrow. You can't borrow from here nor here. So you will borrow from this one. You take it out and you put 1 and 1. These are the borrows. And then you take one of them and you put 1 and 1. And now you take one of them and you put here 1 and also 1. Now you can subtract 2 from 1. And the result is going to be 1. Similarly, here you subtract 1 from 0 is 1. Here you subtract 1 from 1 is 0. Now, this one is already taking out. So 0 from 0 is 0. And now you subtract 1 from 0 is 1. And now, to generate this, if you want to subtract 0 from 1, you can't. So you need to get an end borrow, and you cross it out, and you have 1 and 1. 2 subtracted from 1 is equal to 1. And you notice that you have this end borrow. Because of this, the result that you had here, you put it right here, and you put this number 1 followed by zeros, indicating 2 to the power of 8, since you have 8 bits. And you do the subtraction here again, and you can notice that this subtraction is special, because it's actually, this subtraction is the definition of the 2's complement, and we will see this in a future slide. I did the subtraction here. If you want to subtract this number from a certain other number, you do it using the borrow idea, or you could do it in a simpler way by taking the 2's complement of this number. And we already discussed this. To take the 2's complement is you put 0. Any 0 you have, you just copy it until you find the first one. You copy it, and then you start flipping. The 1 goes to 0, the 1 goes to 0, the 0 goes to 1, so go to 1, the 1 goes to 0, and the 1 goes to 0. And this would be the correct result. And you have to have an indication that this is a negative number. This is a negative number. This is the unsigned binary subtraction. Now, the subtraction 2 to the power of n minus x is taking actually the 2's complement of x, as we discussed. To do both now, the unsigned addition and the subtraction bundled together, you would do it this way by applying the idea that we just found for the subtraction. You have a binary adder of 4 bits and another 4 bit. You have the binary adder. You could have the ripple adder or the carry look ahead adder in this box, and you generate a 4-bit result for this one. The subtraction, you would have a binary subtractor between the A and B. Now, you know that you might have the correction step based if you have an end borrow or not. If you have an end borrow, then you need to do the complement, the 2's complement. If not, then you just pass it the same. And now, at the end, you have to choose between the addition and the subtraction based on the operation that you have. If you use subtraction, then and now that you can see the subtraction doesn't have a bar, so you will get these results and you pass them out to the final result. If you want to this one, which is the addition, notice that you have a bar here, then you will pass the result. Actually, this is what we studied before, which is a multiplexer. A multiplexer where this is the selection line, and it selects between the result of the addition and the result of the subtract. Now, this is actually quite complex. And actually, we did the subtraction in a tedious way. So our goal is to try to design a shared, simpler logic for both addition and subtraction. And to do this, we will revisit the complements, and after that, we will notice a simple manipulation to convert the subtraction into addition, and we will find that the end up block diagram is super easy compared to this big block diagram. Now, the complement, we studied that we studied the ones complement and also the twos complement. Now, the ones complement is actually of any number n is actually 2 to the power of n minus 1 subtracted from n. While the twos complement is 2 to the power of n only subtracted from n. This is the definition of the first and the twos complement. Now, to take an example, if n is this number, which is having 8 bits or 8 digits. Now, 2 to the power of n minus 1 is 255. 2 to the power of n is 265. Now, the 255 in binary representation is 1111, 1111. The 265, which is one more, notice that the twos complement is the ones complement plus 1. It will have 0, 0, 0, 0, 0, 0, 0, 0, and 1. And you can check this. If you add 1 here, if you add only 1, and you try to do the addition, you will end up with this result, because the twos complement is the ones complement plus 1. Now, we generated the binary representation using ones complement and using twos complement of 2 to the power of n minus 1 and 2 to the power of n. Now, to get the ones complement of this number, the one that we have, we take the 255 and we subtract it from this number. To do the subtraction, now the subtraction is super easy. You don't need to do any borrowing because you have ones all the way. So 1 minus 1 is 0. 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 1 minus 0 is 1. 1 minus 0 is 1, and so on. Now, since the 2 to the power of n minus 1 factor consists of all the ones, and since 1 minus 0 is 1 and 1 minus 1 is 0, then the ones complement is simply you flip each bit. So if you have this number, you flip it. You flip every bit. The 1 becomes 0, the 1 becomes 0, the 0 becomes 1, the 0 becomes 1, the 1 becomes 0, the 1 becomes 0, and so on. And this is what we studied before. That the ones complement for a binary number, if you want to generate the ones complement, you simply flip all the bits. Now, for the twos complement, we will subtract this number now. It's different than ones complement from our number n. Now, to do the subtraction, you will notice that you need to borrow this end one. You need to borrow it into everyone. So you take this out, and then it will become 1 and 1 and 1 and 1 and 1 and 1 and 1. And the last one you have 2. 2 minus 1 is 1. 1 minus 1 is 0, and so on. Or you will notice that the result is actually the ones complement plus 1. This is what we said, which is a fact that can be used in designing the hardware later. That we know that to get the twos complement, flip all the bits and then add 1. Or we gave you the second idea of finding the twos complement by beginning at the least significant bit, which is the rightmost bit. You begin from this bit, the right one, and then if you copy all the least significant zeros and you copy the first one. In this number, we found the 1 right away, so we copy it. And then after that, you start flipping. You complement all the bits thereafter. So the 1 becomes the 0 becomes 1, and so on. So this is a revision of the complements. Now, how to do the subtraction with the 2's complement? Now, the idea is simply we convert the subtraction into addition. We convert the subtraction into addition. Now, if we do this conversion, we don't need to worry about borrows anymore. So for an n digit, an unsigned number, m and n, if you want to do the subtraction, m minus n, which is m minus n, as you can see here, you add the 2's complement to the subtrahend n. So you get the 2's complement of the subtrahend n, and you add it to the minus n, meaning that you will get the 2's complement of this number. Since it has the negative here, the subtraction, you convert this subtraction to addition, and you get the 2's complement of this number. Now, the 2 complements of n, you can revisit the previous slide. To get the 2's complement, it's actually 2 to the power of n minus. And now you just add. To add those two, you get this number, which is m minus n plus 2 to the power of n. Now you have two cases. If m is larger than or equal to n, an end carry. Now we are talking about carries because we are working with addition. If an end carry 2 to the power of n, if m is larger than n, an end carry 2 to the power of n will be definitely generated. So m minus n remains, which is the correct result. Now, if m is less than n, an end carry will not be generated. So what remains is this value, but I rewritten this value to see that this n minus m is actually the 2's complement. So we get the 2's complement of this value to get the correct result. So to correct the result, we obtain this value, and then we take the 2's complement of the result and place a negative sign to indicate that the result is negative. To check this, I make it simple for you to understand. We got two examples. The first example where an end carry is generated, and the second example where an end carry is not generated. So you want to subtract those two numbers. To do the subtraction, now we are not going to worry about the borrow anymore. We will convert this subtraction to addition, and we will generate the 2's complement of this number, the second number. To the 2 complements, we put the first one as is, and then flip the rest of the bits. 0, 1, 1, 1, 1, and then 0, 1. Now you do simple addition, the way that we studied. 0 plus 1 is 1, 0 plus 0 is 1, 1 plus 1 is 0, carry 1, 1 plus 0 plus 1 is 0, carry 1, 1 plus 1 plus 1 is 1, carry 1, 1 plus 0 plus 1 is 0, carry 1, 1 plus 1 plus 0 is 0, carry 1, and the last one is 1 plus 0 plus 1 is 0, and the carry 1, and this carry will be here. This last carry is the end carry. And since we have an end carry, it's indicating that the remaining bits here is the correct result. The carry of 1 indicates that there is no correction, and the result is this one. And you can see that if you subtract those two numbers, try to convert this to decimal. If you convert this to decimal and you subtract it from the decimal representation of this number, you do the subtraction, you will find that the result is equal to the decimal representation of this number. Now, the other example, same idea. We convert the subtraction to addition. We take the 2's complement. We copy the first two zeros, and we copy the 1. We face the first one. After that, we flip the rest of the bits. The 0 becomes a 1, and so on. Now, we do the addition. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and there is no end carry. No end carry. Meaning that we need to correct this result. to correct. Now the carry of 0 indicating that a correction of the result is required. And to do the correction, you do the 2's complement of the result. You see this result here? You do the 2's complement to get the final result. So you keep this one as is, and then you flip the rest of the bits, as you can see here. And this would be the result, but you add a negative sign to indicate that this is a negative value. Notice if there is no correction needed, meaning that you have an end carry, you do the 2's complement only one time. When at the beginning you want to convert the subtraction to addition. If there is connection that is required, you do the 2's complement 2 times, here and here. You do it first to convert the subtraction to addition, and you do it again another time to correct the result. Now, because of this idea, we can combine the addition and subtraction together. And the idea is, let's suppose that we want to add two numbers. To add two numbers, we will make the selector S. You could also say subtraction. Since we want to do addition, the subtraction would be 0. Now what happens is, this 0 will go to the carry n, because we just want to add two numbers, and at the beginning the carry would be 0. And this 0 will also be the input to these XORs. Now the job of the XORs is either to have the B as is or complemented. In this case, since this input is 0, the B will be the same. And this is one of the properties of the XOR that we studied also in a previous lecture. And now you do the addition of A and B simply by using this ripple addition or the ripple adder to generate the sum and the carry. Now, if you want to do the subtraction, now we will convert the subtraction into addition. How? By taking the second number, which is the B's, and get the 2's complement of them. We get the 2's complement of the B. To get the 2's complement of the B, you need to flip all of them by having the subtractor now is equal to 1. So there is a 1 here. And if you flip all of them, you will have B0 bar, B1 bar, B2 bar, and B3 bar, generating the 1's complement of B. But we want to convert from the subtraction to addition, we want the 2's complement. Here we generated the 1's complement, and we added one more by having a 1 in the carry. Now this one, in combination of flipping the B's, is actually the 2's complement of the B. This is the 2's complement of the B, and you do simple addition to get the result. Now, this is a very simple design where you have the ripple adder that we studied before. We just added these XORs to get the 2's complement. That's the first idea here. We added the XORs to flip the number, to flip the bits of B. And we also make use of the carry in the first full add. The input carry here, if you want to do addition, it would be 0. If you want to do subtraction, this carry would be 1. And this is basically the idea behind the binary adder and subtractor. Now, this hardware is very critical and important because, as you know, any computer has inside it the CPU, the central processing unit. And one major part of any CPU is an n-bit adder. the n-bit adder in any CPU is actually designed using similar idea as this one. So for example, our processing units or the processor that we have in the market nowadays, they are either 32 bits or 64 bits, meaning that inside the CPU, you will have either 32-bit adder or 64-bit adder. In this example, we have 4 bits. You can repeat this 4 bits many times to generate 32 bits. You'll actually generate them several times, and to get how many repetition that you need, if you want 32 bits, then you would need some number that you need to multiply it with 4. So this number is going to be 8. 4 times 8 is 32. So you need to copy this design 8 times to generate 32. Now, we'll discuss the signed integer representation. We actually just reminding you that we studied before the sign and magnitude. The n-1 digits are interpreted as a positive magnitude. The signed complement with its 2 version, the ones and the twos complement, the digits are interpreted as the rest of the complement of the number. There are 2 possibilities. The ones complement, you use the ones complement arithmetic. In the twos complement, you use the twos complement arithmetic. And you can go back to the previous video that we discussed those 3 types, the sign, magnitude, the ones complement and the twos complement in detail. Now, just a reminder to remind you that this bit here, which is the most significant bit, is the sign bit. If S is 0, then the number is positive. If S is 1, then the number is negative. And the rest of the bits represent the magnitude of the number. Now, if we say that n is 3, meaning 3 bits, now if you have these decimal numbers, which is spanning from -4 to +3, the sign and magnitude representation in the positive, let me break the table into 2 so you understand. Those are positive numbers. And for the sign and magnitude, one's complement and two's complement, we say have the same representation for those numbers. The positive number, we don't have any problem, no change between those 3 models. Now, for the negative numbers, the sign magnitude, you have 1 in the sign indicating it's a negative number, and you copy the magnitude. You have the 0 here, -0. You have the 1 here, you have -1. The 2, you have -2, and the 3, you have -3. You can notice the disadvantage of the sign magnitude. We have +0 and -0. Now, for the ones complement, what happens if you flip all the bits? You have +3. If you want to get -3, you flip everything. If you have 0, you would generate, unfortunately, a -0 by flipping all the bits also. Now, the twos complement is actually the ones complement +1, or you simply generate it. If you have +3, then you keep the first one, and then you flip the rest, which is 0 and 1, generating this number, meaning that this number is -3, and it is actually -3. And you can check the other numbers. If you have the number of bits n is equal to 4, same idea, but the table now is bigger because you have many numbers, and the numbers now spanning from -8 to 7 or +7. As an example, I'll take one example. If you want to generate -5, then in sign magnitude, you will have 1 in the sign, and you will have the magnitude of the number 5101. If you want to get the ones complement, You know that the 5 is 1, 0, 1, 0. This is the 5. To get the 1's complement, you flip all the bits to become 0, 1, 0, 1. To get the 2's complement, you start from the rightmost, you copy the first one, and then you start flipping the rest of the bits here, 1, 0, 1. Now, after we revisited the binary representation using, or the signed number representation using sign and magnitude, 1's complement and 2's complement, we will check the arithmetics of each one of them, starting with the sign magnitude arithmetic. The idea here, if the sign of the three numbers, the two operands and the result is the same, you add the magnitude and check for overflow. And then the sign of the result is the same as the sign of the first operand. Now, of those three numbers, two operands and the result is different, then you subtract the second magnitude from the first. If a borrow occurs, you take the two complements of the result. You make the result sign the complement of the sign of the first operand. Since the signs are different, the overflow will never occur. This is an example of these cases that we discussed. This is the first case. Notice that the numbers now are represented using sign and magnitude. So you have two numbers and you want to add them, and they have the same sign. So you simply add 0 and 1 is 1, 1 and 0 is 1, 0 and 1 is 1, and this is the result. Notice that this is 2, this is 5, and 2 plus 5 is equal to 7. Now, example 2, you have two numbers with different signs, and you want to add them together. So what you are doing is actually you are subtracting. So what happens? You have the same number as is, and the second number, since you have different signs, you are actually subtracting the negative part of this one. So to get the opposite number, you just change the sign from 1 to 0, and you keep the same magnitude. So now you do the subtraction. To do the subtraction, this one or this number is the same, and this number, we know that one way to do the subtraction quickly is to convert the subtraction to addition, and you get the 2's complement of this number. The 2's complement of this number is 1. You keep the first one, and then you start flipping the rest of the bits here. And now you do the addition. 0 and 1 is 1. 1 is 1, 0 plus and carry 1. 1 and 0 and 0 is 1. And 0 plus 1 is 1. Now, this number here is actually minus 3 in 2's complement. But since we are doing the sign magnitude arithmetic, we need to find the equivalent value of it in the sign magnitude. The equivalent value of minus 3 in sign and magnitude, the sign minus is the 1 here, and the magnitude 3 is 1, 1, and 0. Now, another example, you do the subtraction of different numbers, as you can see here. So to do the subtraction, since this is subtraction, you copy the same number, the first number here, and then you will convert the subtraction to addition this way. To convert it to addition, you actually do it directly by having the negative value of this using sign and magnitude, and the negative value using sign and magnitude is the 0 will become 1. You change the sign and you keep the same magnitude. You keep the same magnitude, and then you do the addition. 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1, or this one would be the sign, and we know that the signs are the same here, so we copy the same. We copy the same sign. This is the sign magnitude arithmetic. we will check the signed complement arithmetic too. In the addition, you add the numbers including the sign bit. The two's complement, you discard the carry out. The one's complement, you use an end around carry by adding one to the result. If the sign bits were the same for both numbers and the sign of the result is different, an overflow has occurred. This is for the addition. For the subtraction, from the complement of the number you are subtracting, you form actually the complement of the number that you want to subtract, and then follow the same rules of the addition. Here are examples of the two's complement. And we studied this before. This is a quick revision. 1 0 1 1 added with 1 1 0 0. So you do the addition. 1 plus 1 is 0. Carry 1. 1 0 and 1 0. Carry 1. 0 carry 1. Then 0 carry 1. And this one is here. This carry tells us that the result is correct. Now, this example, you have subtraction. So the subtraction, what you do is you convert it to addition by having the two's complement of this number, which is 1 0 1 1, and then you do the addition here. 1 plus 1 is 0. 0 plus 0. 1 plus 1 is 0. Carry 1. 1 and 0 and 0 is 1. 1 and 1 is 0. Carry 1. And 1 and 1 and 1 is 1. Carry 1, and this one is here. And this one indicates that this result is also correct. This is the signed two's complement example. The signed one's complement example, you see the difference between the previous slide and the next slide. What you do is you have this addition of 1. If there is a 1 generated here of the result, then you add 1 to the result to correct it. Similarly here. Now, from this discussion, if you were asked which one you should use, the sign magnitude or the two's complement or the one's complement, you can see that the two's complement is the easiest. And because it's the easiest, the hardware design will be simpler. And this is why we use the two's complement. And modern hardwares, they all use the two's complement, the representation of the negative number, and they also use the two's complement arithmetic. Now, here are some exercises to do the binary addition used in two's complements, because it's the famous one. This is a negative number added with another negative number, a positive number added with a negative number, a negative number added with a positive number, and a positive number added with a positive number. You can practice the addition of those 3 cases, and you can confirm, because now you know -6 added with -13 is -19, and you see the rest of them as well. Try to practice and make sure that you get the correct results. In each of the 4 cases, the operation performed is addition, including the sign bit. Any carry out of the sign bit position is discarded, and the negative results are automatically in its two's complement form, easy without troubles. Now, if you want to do the subtraction, here are 2 examples. If you want to subtract +6 subtracted from -13, or -6 subtraction of -13, this is the end result, and you can check them as you can see. I will only do this here. This is -6 representation in two's complement. This is -13 representation in two's complement, and you want to do the subtraction. So you make it an addition, and you take the two's complement of this number. The two's complement, you copy the first one, and then you start flipping. And then you do a simple addition. 1 plus 0 let's do it completely. If you have a carry and 0, 0 plus 0 plus 1 is 1, and carry 0. 0 plus 1 plus 0 is 1, carry 0. 0 plus 0 plus 1 is 1, carry 0. Now 0 plus 1 plus 1 is 0, carry 1. And similarly here, you'll have 0, carry 1, 0, carry 1, 0, carry 1, and then 0. And you have an end carry, this end carry 1, indicating that this is the correct result. And you can see that the result is 7. Now, again, we are visiting this since it's very critical and an important component of any processing unit. The two's complement, adder and subtractor, is the one used in all the hardware. The subtraction can be done by converting it to addition of the two's complement of the second operand. You complement each bit, you're doing the one's complement, and then you add 1 to the result by adding this 1 in the carry. The circuit shown are computing a plus b and also a minus b. For s is equal to 1, you subtract the 2's complement of b, that is formed by using XOR to generate the 1's complement, and then you add 1 applied to C0. For S0, you do simple addition, and the b won't be changed after the XOR. Now we will discuss the idea of the overflow that could happen in addition and also in subtraction. The overflow occurs if n plus 1 bits are required to contain the result from an n bit only addition or subtraction. So you cannot accommodate the n plus 1 bits in only n bits space. The overflow can occur for addition of 2 operands with the same sign or subtraction of 2 operands with different signs. Now, let's check the correct operation. The sign number cases with correct result signs, you can see if you add 2 numbers with positive signs, with negative signs, and the answer is negative. Or if you add 2 numbers with positive signs and the result is also positive, the result would be correct. Similarly, if you take a number that is positive and subtract it from a negative, and the result was positive number, then it's okay, and the result is correct. If you subtract a negative number from, or you do the subtraction between this negative minus this positive number, the result is, and the result is also negative, then the end result is also correct. Now, this detection that we checked can be performed by examining the result signs, which should match the sign of the top operand. So you can see those operations, whether it's addition or subtraction, you check the result. If the result sign match the first operand, then it's okay. Similarly here, if the result match the first, okay. The result sign match the first, then it's okay. The result match the first is also okay. Now, to try to find the hardware that perform the overflow detection using the carries, we check the signed number cases with carries Cn and Cn minus 1. So the carry at a certain stage and the carry before that. And those carries, we observe them, and they are shown for correct result sign. As you can see, this is the same thing that we found in the previous slides, but now we added the carries in the stage Cn and in the stage Cn plus 1, or as we indicated here, if we assume that this is Cn minus 1, this one would be Cn. Now, since the operation could be addition or subtraction, those carries will follow the operation itself. So let's see it for the addition. For the addition, you could say that 1 plus 1 plus 1 is equal 1, carry 1. 0 plus 0 plus 0 is equal to 0, carry 0. For the subtraction, we discussed two methods, either using borrows or converting the subtraction to addition, and you will find that those carries would be 1 and 1 and 0 and 0. Now the sign number cases for these carries, Cn and Cn minus 1, but shown for an erroneous result sign because of the overflow, would be like this. Now, for example, for the addition, if you add 0 plus 1 plus 1, the result is 0, carry 1. 1 plus 0 plus 0, the result is 1, carried 0. Similarly, if you try to do the subtraction for those numbers, those are the generated carries. Now you can see that there is an overflow because when you compare to this, the sign of the result to the sign of the first operand, they are different in all of these cases. So now we have those 8 cases where 4 of them give no overflow and 4 of them gives an overflow. Now, if we look only at the carries, you will notice that if the carries Cn and Cn minus 1 match, 1 and then 1, 1 and then 1, 0 and then 0, 0 and then 0, then there is no overflow. However, if they differ, 0 and then 1, 0 and then 1, 1 and then 0, 1 and then 0, there will be an overflow in the result. So the simplest way to implement an overflow diction called V is equal to the XOR of this digit, this bit, with this bit. So it's Cn XOR Cn minus 1. This works correctly if only if the ones complement and the addition of the carry n of the addition of the carry n of 1 is used to implement the complementation. Otherwise, it has some issues. So if you do the subtraction this way, this overflow will be this overall detection would be correct. So the hardware design for it is simply, if you implement the n-bit adder / subtractor using one's complement and then you add 1 into the carry n, and you found you just get a line that represents the previous carry Cn minus 1 and the carry Cn, and you XOR those together to check if there is an overflow or not. If V is equal to 1, then there is an overflow, which is a bad sign. If V is equal to 1, there is no overflow. Everything is okay. That's the overflow detection circuit, which is a simple XOR, gate added to the n-bit adder / subtractor. To show you where exactly you put this XOR, you can go back here and to this design, and you found that this is the carry 3 and this is the carry 4. You take this one and this one and you put them with an XOR gate to find the overflow detection. Very simple addition to gain a very good property, which is the overflow detection. Now, after this, we finished completely the addition, the subtraction, and also the overflow that happens if the result has some troubles. The overflow detection circuit tells you if there is a problem or not. Now we will move to the binary multiplication. The binary multiplication is fairly easy. If you have two numbers, let's say they are 5 and 12, 5 being the multiplier, 12 being the multiplicand, you get the binary representation for them. You do the multiplication the same way that we studied in elementary school. 1 times 0 is 0. 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. And then we shift. 0 times anything is actually zeros, which tell us now something fairly easy. If the multiplier bit is 1, then you copy the same multiplicand. If the multiplier if the multiplier bit is 0, then you zeros everything, and you keep shifting as we studied. Now, after you find all the partial products, since the multiplier have 4 bits, you will have 4 partial products. And now you do this simple addition. 0, you just bring it down. 0 added with 0 is 0. 1 and 0 and 0 is 1. 1 and 0 and 0 and 0 is 1. 1 and 0 and 0 is 1. Sorry, had 0 and with 1 and 0 is 1. 1 and 0 is 1. 0 goes down, and also this 0. And you can see that this is the decimal, or this is the binary representation of the decimal number 60. 5 times 12 is 60. And this is called the product. Now, we use the Boolean AND function to multiply the bits. If you AND 1 with 0, you will get 0. If you AND 1 with 0, again, you get 0. If you AND 1 with 1, then it's 1. If you AND 0, whether it's 0 or 1, you will come up with zeros. So it's the simple AND function. Now, you should notice that if you have an m bit multiplied by n bit, you produce an n time, you produce an n m bit partial product, an n m bit partial product. So you have an m bit, an m bit, and also m bit, and there are n count of them. N count of them. The sum of these products, which is the final product here, have an m plus n bit product with a possible of a carry out. You can see here, you have 4 bits and another 4 bits. 4 plus 4 is 8, and you have 8 bits in the results. Now, to implement the binary multiplications, there are many methods. One of the simplest methods is a direct implementation of the partial products. This idea is called an array parallel multiplier, or simply an array multiplier. If for 6 bits and you have x0, x1, x2, 3, 4, and 5, you want to, this is the multiplier. The multiplication is y0, y1, y2, y3, y4, and y5. You generate those partial product by ANDing x0 with each one of the y's, and then x1 with each one of the y's, and so on. And you keep shifting. You keep shifting. The partial products will be P0 up to P11 in this case. Since you have 6 bits and 6 bits, then 6 plus another 6 is going to be 12 bits in the partial product. Now, to implement this, you have the AND gates, so you can replace this one actually by x0, y1, for example, and you put an AND gate here to represent this one. To keep the figure short, we just keep them this way, indicating that there is an AND for each one of them. You start from x0, y0 to x0, y5. Actually, I'm copying this line here. Similarly for the next one here. And so on. this one here, and you can keep doing this. Now, to do the addition, you can see that the partial product P0, the partial product bit P0, is directly X0, Y0. Now, the next partial product, you need to do an addition between those two bits. And you do it by using a full adder this way. It has 3 inputs. One of the inputs will be 0. This is why we have 0 here. Because in any full adder, you have 3 inputs. One of them would be 0. And you do the addition and you generate P1. Now, notice that we use the ripple adder here. This is a simple 6 bits, or 1, 2, 3, 4, 5, 6 bits adder. Each one of these adders having the 3 inputs and generating 2 outputs. One of the outputs is the partial product, which is the sum, and the other one will be the carry input of the next adder. And you keep adding those 2 with the resulting carry n, adding those 2 with the resulting carry n, and so on. You can see that we have an iterative array where this is your cell. Let's take one from the center. This would be your cell. And you repeat it everywhere. You can, to be that exact, this is your cell. And you repeat it everywhere. You repeat it. So this is the cell, and you keep repeating it everywhere. There are special cases around. For example, at the end here, the carry output of the last digit here is actually one of the inputs of the next adder. So one of the input is here. And you keep doing this for the last adders. Also, at the beginning of each row of these adders, you have a carry input 0. You have a 0. And you see those zeros are here. The adder at the begin, this corner here, it will have only one bit. That is X1, Y5, and you have a carry input of 0, indicated by this 0. And you keep doing the addition. You will get P0, P1, P2, P3, P4 this way, and you will find that P5 has this chain of adders this way. Also, P6 have this chain of adders, which is the maximum number of adders vertically, and it will be reduced to generate the partial product tree. So simply, the array multiplier is a direct implementation of the partial product, where each digit is actually a symbol added. There are other implementations of the same idea, but we will only focus on this one. This is for the array multiplier. This array multiplier area is huge, but it's fast compared to other types. Now we will check other arithmetic functions, such as incrementing, decrementing, multiplication by a simple constant, division by a constant, and the zero fill and extension. To do these functions, we have to introduce the idea of contraction. We'll do that in probably the next slide. It's convenient to design the functional block by contraction, as we said, which is by the word contraction, we mean we remove, or it's the removal of redundancy the redundancies from a circuit to which we have value fixing for some parts of the hardware that were applied either in a direct input or an input of an internal gate. To show you the idea of contraction, the design by contraction is the technique to simplify the logic gates in a certain functional block to implement a simpler different function. The new function must be realized from the original function by applying rudimentary function to its input. Either you fix the value, or you pass it, or you invert it. The contraction is treated here only for application of zeros and one, not x and x bar. After application of 0 and 1, equations or the logic diagram is simplified by using rules given in your text book, but we will show you those rules in the following diagram. Designed by contraction example, the contraction of a ripple carry adder to build an incrementer for n is equal to 3, to build an incrementer. But now we have this example where n is equal to 3. So you have a 3-bit ripple adder. You have S0, S1, and S2, 3 bits. And you want to do a simple incrementer. A simple incrementer. Now, the incrementer, the second operand would be 1. So if you have the first operand a, and you want to increment it, you will add 1 to it to generate a plus 1. So if you have a as a0, a1, a2, this is 3 input a, this incrementation by 1 is actually of the form 1, 0, 0. And then you will get the result in S0, S1, and S2. You keep the a as is. You can see that this is the 3-bit incrementer where you have half adder, another half adder, and the OR gate. Similarly here and here. So this is a full adder, a full adder, a full adder, and you have the carry output of this one as a carry input to the next one. The carry output here is the carry input as is here. And you can check the ripple addition if in case you need to refresh your mind. Now what happens, we have the same idea that we described here. We have the A, A0, A1, and A2. Now B is replaced by 1, 0, 0. So you have 1 here, 0 here, and 0 here. Also, the input carry at the first stage is actually only equal to 0. Is equal to 0. Now, by having this value fixed, we can simplify the circuit. Because now we know since this is 1 and it's passing through the XOR will behave like a buffer. The XOR will behave like an inverter. So you can cross this XOR and we make, instead of this XOR, a simple inverter. A simple inverter. Now also, since you have a 1 here, as one of the inputs of the AND circuit, whatever comes in the second operand, which is A0 in this case, will go directly to the output A0. So you can cross the and replace it by a symbol line between this input and this output. Now, because you have the carry N0 right here, so this 0 in the XOR indicate that this line goes directly to this line. A 0 in the AND gate here completely take this out and generate a 0 right here. Because 0 ANDed with anything is going to be 0. Similarly, 0 ORed with anything will have this line that comes from the AND going directly right here. So you can see that, you can say that we generate, instead of having those 5 gates, this XOR will be replaced by just an inverter going directly, this inverter going directly this way to the sum, going directly to this sum. You can continue this to the next number of bits, but we will first check the blue box here. How do we generate it? To generate this blue box here, We try to redo this same thing here, but now we make it simpler by having an inverter here. And we know that this inverters go directly to S0. Since this XOR will be removed, one of its input is 0. And we have a symbol line going through this and going through this OR to the next carry over here. And by having those two lines, we have this, or those two paths, we have this block. And this is the idea of contraction, which is simplifying a bigger gate to design a different, simpler function, which is just an incrementer. Now, we do the same here. Now, we no longer have a 0. We have a carry 1. So some of the gate will keep them. Since we have a 0, this 0 will be directly going through the XOR. So we take out the XOR. And since we have this 0 going here, this 0 will be one of the operands of this AND circuit, which will cross this AND completely. Now, this carry will go through two paths through this XOR. We still keep the XOR, and we will only have a line instead of this AND. So we simplified this XOR by a line, and we crossed this AND completely. We are left over with this AND here, and with this XOR here. Now let's check this OR. Should we keep it or not? Since one of its input is 0, we can replace it by a symbol line over here. Now, similar idea here. But since we have a 0 going through this, and we have a 0 also going through this, we should end up with the same circuitry as this one. But we took out this AND gate since we have the output going from here and passing through this AND and this XOR. You noticed here that you generated the same inputs here and here. You can see that we have the carry going through here, and also the A going through here. So we have the same X and X, or together will generate the same X, where this carry would equal to X. So we can take this OR gate and we simplify the last bit using the idea of the contraction this way. So now you can see that this idea of contraction making the circuit simpler. The whole circuit here is just an equivalent of an inverter with some lines. The equivalent of the circuit in the middle of a ripple adder is a half adder, which is AND and XOR. And this could be repeated if you have this middle still can be repeated to make the incrementer within more than 3 bits. You would repeat this part. The last one is a special case of the middle part where this behavior happens. You can take out the OR, since you will have the same inputs here and here, and the generation of the same input and the inputs of the OR gate happens because of the idea of propagation. And we studied the propagation when we talked about the look-ahead adder. And if you want to check how we generate this one in more details, you can see it in your textbook. This is the design by contraction, and we took the ripple carry adder as an example. So incrementing and decrementing. Incrementing, adding a fixed value to an arithmetic variable. you fix value of the first bit position to be 1 and the rest are 0. If you want to count up, some example as an incrementer, if you can increment a by 1, you can increment another variable b by 4, and so on. And each one of them will have a different contraction. We had the example a plus 1 in the previous slide. The function block is called an incrementer. You could have an incrementer by 1, incrementer by 2, by 3, by 4, and so on. Decrementing, what you do is actually subtracting a fixed value from an arithmetic value. Your fixed value is often 1, so increment or decrement by 1. This is also called counting down. So if you increment by 1, you are counting up. If you decrementing by 1, you are counting down. The functional block is called a decrementer. It could be a decrementer by 1, by 2, by 3, and so on. Now, the multiplication and division by a number this number is a constant. So if you want to multiply by a number, let's say 4, you should know that if you shift any number, let's say in this example b, so if you shift b to the left by 1 position, it's like you are multiplying b by 2. So if you make b like this, you shift it to the left by 1 position. It's like you are multiplying b by 2. So this is the original b, and now this is the resulting b after shifting by 1 bit. This number is the original b times 2. Each time you shift by 1 position, you are multiplying by 2. So, for example, if you want to multiply the number by 4, we know that 4 is actually 2 to the power of 2, which means that you need to shift to the left by 2 position. So you shift the b to the left by 2 position to multiply by 4. If you want to divide by a constant 4, then you do the same operation, but right now you are shifting to the right. You are shifting the b to the right. If you shift b to the right by 2 position, then this means that you are dividing by 4. As a general rule, for multiplication, if you shift to the left, by n position, let's say n positions, this means that you are multiplying by 2 to the power of n. Similarly, if you shift a number to the right by n, this is equivalent to dividing the number. Here you are multiplying the number by 2 to the power of n. Here you are dividing the number by 2 to the power of n. Now, let's say you want to multiply b, being 4 bits, by the number of 5. Now, we know the power of 2 is 1, 2, 4, 8, 16, and so on. So if you want to multiply by 1, you don't shift at all, because this is 2 to the power of 0. This is 2 to the power of 1. This is 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on. If you want to do multiplication, if you want to multiply by 1, you keep the number as is, no shifting. If you want to multiply by 2, you shift to the left by 1. If you want to multiply by 4, you shift to the left by 2, and so on. You want to multiply by 8, you shift to the left by 3. You want to multiply by 16, you shift to the left by 4. However, what if you want to multiply by a number that is not power of 2? For example, here, 5. So what you do is you break down the 5. You know that b times 5 is actually b times 4 plus 1. You know that 4 is a power of 2. And you could get b times 4 by shifting the b to the left by 2 positions. This is the blue 4 times b. And then you add one more b, which is the red one, a version of b as is without shifting. We got this idea by distributing the b to the sum, 1 plus 4. So you have 4b plus another b. And then you do simple addition. So you have a version of b added to the version of b that is shifted to the left by 2, which indicates b times the constant 4. And then you do the design in hardware simply by generating b0 directly, b1 directly, and then you sum up those 4 digits with 4 digits using a 4-bit adder this way. You will generate a sum, 4-bit sum with a carry in the output, and these will be the results of multiplying b by a number that is not a power of 2. Now the last 2 ideas is the zero fill and the extension. They are very close to each other. The zero fill, you fill an m-bit operand with zeros to become an n-bit operand with n larger than m. So let's say that you want to have this bit number that has 1, 2, 3, 4, 5, 6, 7, 8 bits, and you want to fill it to 16 bits. You make it 16-bit if you fill the most significant bits with zeros, you generated 16-bit this way, or you fill the least significant bits with zeros to generate this 16 bits. So you actually do this idea, the zero filling, either to the left of the number, where you fill the most significant bits, or to the right of the number, where you fill the least significant bits. So filling usually is applied to the most significant bit end or the least significant bit ends. Each one of them have their indications, Sometimes you need to fill these with zeros, sometimes you need to fill these with zeros. Now, the extension means increasing the number of bits at the most significant bits end only of an operand by using a complement representation. This happens when you are dealing with numbers. So if you have a number that is 8 bits and you know this number is positive, to make it 16-bit and you still keep the same value of the number, you need to extend the sign. You extend the sign. If it is 0 indicating a positive number, you extend zeros. If it is a negative number, then you extend ones to generate their 16-bit version.